In this video, I'm going to demonstrate how you can apply Benford's law to look for fraud in your numbers. I'm going to use Microsoft Excel to do this. And I'm going to start by explaining a little bit about the history of Benford's law. It started in 1881 when a fellow named Simon Newcomb was thumbing through a book of logarithm numbers. And he noticed that the page numbers towards the front of the book were smeared more than the page numbers at the back of the book. In fact, the page numbers were consecutively smeared less and less as you went through the book. They were smeared most on page 1. And so it got Simon Newcomb thinking about why this might happen, and he actually postulated a formula that would explain this phenomenon, and he published an article in 1881 on this, to this effect. Nothing happened for about 58 years until Frank Benford came along and read that article. And he thought to himself, wow, there must be something to this. I'm going to test it. And so Frank Benford went out and he grabbed 20 different sets of values. For example, he grabbed the surface area of 335 rivers, then 3,259 U.S. populations, some molecular weight numbers, some entries in a mathematical handbook, and so on. And he then conducted experiments and tests against these numbers using the algorithm that Simon Newcomb had postulated. And here's what Benford found. Benford found that there is a pattern, that if you take the first digit in any group of numbers that's created, you find that the first position of those numbers, the first digit of those numbers, is 30.1% of the time is the digit number 1. And 17.6% of the time is the digit number 2. And 12.5% of the time is the digit number 3, and so on. Then if you plot this, here's what you get. I've got the chart here, Benford's law chart, and it shows you the occurrence of the digit 1, the digit 2, the digit 3, and you can see a curve. And this curve kind of slopes downward deeply at first, and then more gradually as it comes. It kind of reminds me of this picture here. And this picture is from the free fall ride at the Atlanta Whitewater theme park. And when you slide down, at first you slide steeply down, whoa, and then you level out towards the bottom. You get to the end, you come out and you fix your bathing suit. And so that's what that reminds me of. And so Benford came up with this law and wrote about it. Then in 1972, a guy named Hal Varian came around and read that article and suggested you might be able to use Benford's law to detect fraud, but he didn't go as far as to try that. In 1999, a person named Mark Negrini became the first person credited with actually applying Benford's law in a search for fraud. And that's the history. Now let's look at the application. Now I've got numbers that I got from the web, from the World Bank, and it just shows the populations of all of the countries of the world over the last 10 years. Let me show you that website. Here it is. I just went to the worldbank.com. I copied all of these populations for the last 10 years, and I pasted them in Excel. So what we have here are some legitimate numbers that were created, and we're going to run Benford's law against them so you can see how it's done and so you can see the results. Now the first thing I'm going to do is replicate the column headings across the top of the page. So here we are, 2006 through 2015. The second thing I'm going to do, let me zoom in a little bit so you can see this a little better. I'm going to write a formula that extracts the first digit of each number using the equal left function. I'll point over to that first number in cell B5, comma, put the number 1, and that extracts the first digit. So there's 25,183,000 people in 2006 in Afghanistan. You can see the formula that pulls that number out is equal left. That means go to cell B5, start at the left, and give me the first digit. That's what that formula really is saying. So once I'm here, I've pulled out the number 2 because 25 million starts with the number 2. Now I'm going to copy that over and double click to copy that downward. And now what I've done is I've replicated that equal left function to extract the first digit of all of these numbers. And that was fairly easy to do. The next step is I'm going to count. I'm going to number 1 through 9 by using the fill handle. And I'm going to use the count if function, equal count if, and it's asking for the range, and the range is going to be all of these numbers I've extracted. In, down, paints the entire range. I hit the F4 key to anchor that range with dollar signs, comma, and then I'm going to point to the number 1. And so this formula I have created is count if. Look in the range, which I've highlighted here, the range of data we extracted. Look in that range and count if it matches what's in W5. And in W5 is the number 1. So count if it's a 1. 625 times there is a 1 that appears. And then I double click the fill handle to copy that downward. And now we've counted the occurrence of all of the digits. And you can see that. Let's chart it now so we can tell visually. So we'll chart that with a column chart, 3D column chart, and there you go. And we can see that without a doubt, this follows Benford's law, Benford's curve. You can see that it starts off sloping downward, and 5 is a little bit of an anomaly here. You've got more 5s than 4s, which is a little strange, but not out of the realm of what Benford would predict. And you can see that these numbers do confirm that there's no fraud going on here, that these numbers all suggest that they are legitimate numbers. Okay, now let's talk about why that would be. Why would the digit 1 occur more often in the first position than the digit 2, and so on? And Benford explained it. He said it's easier to own 1 acre of land than 9 acres. You have to own 1 first before you can own 9, or you have to own 11, 12, or 13, or 14 first before you can own 99 acres, or 91, 92, 93 acres. And so when you count anything you count, whether it's money, whether it's acres, whether it's surface area, you have to get to the 1s first before you can get on, plow all the way through the 9s. And so when you count anything, the 1s are of course going to show up first, and the 9s may not show up at all. And so we get this curve. And now let me show you how you can read it. I'm going to move this down a little bit more right here. And I'm going to change our numbers from U.S. populations to random numbers, so you can see the difference. So I'm going to type in equal rand times 10,000, and that'll give me a random number between 0 and 10,000. And there are the numbers there. So I have just created random numbers instead of U.S. populations. And how do you think this would affect the chart we just created? Well, let's take a look. Here we can see the chart no longer follows the Benford curve. You can't slide down that. That's not a waterfall slide right there. Let's hit F9 to recalculate. And you can see after I recalculate that almost every digit has an equal chance of being the first digit. So it's not following Benford's law. I'll hit F9 again, and again, and again, and again, and again, and again. And we get a lot of different patterns here, but at no time does the pattern suggest what Benford says you will find if the numbers are legitimate numbers and not fabricated numbers. F9, 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 F9. And we do see some weird patterns going on, and I have to tell you, my population in this case is not really that big. Benford would be the first person to tell you your population has to be large enough so that you wouldn't have anomalies in the data, and this is a pretty small set of random numbers. But still, I think you can see the point very easily. And so in this particular case, with random numbers, you're more likely to get a bar chart that is level across the top. You know, there's a little bit of fluttering across the top, but all numbers seem to have an equal chance of being in the first position. Now, this makes me wonder, back in 2008, when Bernie Madoff famously created fictitious data to hide the estimated $65 billion scam that he perpetrated on the American people, the largest scam in the history of the world, $65 billion. Well, the largest scam if you ignore Social Security, maybe. Sorry, that's just a joke. Anyhow, how did Bernie create those numbers? Did he use a random number generator like the one I just showed you in Excel, or did he type the numbers on his keyboard? If he had typed his numbers on his keyboard, then his pinkies would have been on the 1 and 9 position and would never have repeated use. But his numbers in the middle of the board, the 4, 5, and 6 position, or the 5, 6, 7 position, probably would be repeated more as the index fingers from both hands would touch those numbers. And so you would get a bell-shaped curve. You would end up with something more along the lines. So if you hit some random numbers here, you might have hit the 3 and the 9 3 times, and the 8 and the 2 3 or 4 times. And then you might hit some of these numbers in the middle more times than that. Let's just put some more numbers right there. And you get more of a bell-shaped curve. You see this curve? And that would be an indication that, you know what, someone probably was using a keyboard and was just going tap, 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 just to quickly make some fictitious numbers. And in that particular case, that might be what you see. Now, Benford's law is never going to completely prove or completely disprove that information is fraudulent or not. It's just merely a backup suggestion. If you have suspicions about numbers, you might run Benford's law against them to see how, if Benford's law can confirm that they do look legitimate. And if not, that might suggest to you that perhaps you should do more investigation. Maybe you should ramp up your TFT work. Maybe you should ramp up your confirmations if you're on the audit trail. Maybe you should do more, take more effort to look into the legitimacy of the numbers if they don't obey Benford's law. The last comment is this only works on data where every digit 1 to 9 has a fair chance of being selected. For example, if you had the heights of basketball players, you would not have a good set of data to run Benford's law, because there are no 1 foot tall basketball players or no 9 foot tall. Everybody's usually either 5 foot or 6 foot something. So the 5 and 6 would occur in the first position. So as an example, your data has to have data which starts at numbering 1 and has the opportunity to go up to 9. But hopefully you've got a little bit more information now where you can roll up your sleeves and apply Benford's law to your benefit in the future. Thank you.